Okay, so here we go again. Example 3 says define a sequence a1, a2, and so on, such that, a0 is 2, a1 is 9, and so on and so forth. So this is how the sequence is defined recursively, and this formula works for any k greater than or equal to 2. We want to use strong math induction to prove that the formula that generates the terms in the sequence can be this formula, basically. So again, we're going to start with strong induction, and we're going to say let n be an integer that's greater than or equal to 0. And for the base case, how many base cases do we have to test out? So just like in the previous video, we said that the distance from k to k minus 1 is 1 step. The distance from k to k minus 2 is 2 steps. We take the greater amount, which is 2. That tells us that we need to test 2 base cases, starting with 0, because 0 is the start of the domain. So the first step is to check how much is a0. This is 2. And the next thing we want to do is test out if this formula generates also 2. So 5 times 3 to the power of 0 minus 3 times 2 to the power of 0, is that really in reality equal to at the end 2? And again, I'm putting zeros because the n is supposed to be 0. So if I did that correctly, I'm going to end up with 5 minus 3, which is exactly 2. So far it looks like the answer matches. So far the theorem is true. And so take a minute to see if you can go ahead and do the next base case. So the next base case is n equal to 1. Okay, so there it is, the second base case when n is equal to 1. We end up with 9 for the first term because of what they were told at the beginning. And then if you use the 1 and plug into the recursive formula, you get also 9. So it seems like the base case is working out, and now onto the inductive hypothesis. So what are we doing in the inductive hypothesis? So in the inductive hypothesis, we're assuming that ak is actually going to be equal to 5 times 3 to the power of k minus 3 times 2 to the power of k for every n from 1, 2, 3 all the way to k, where k is some random integer. Basically, we're assuming that the theorem is actually going to hold for all the numbers from 1 to k. And we want to show that the theorem actually holds for the next case. So that looks like this. So to prove this, we're going to do the same thing that we did previously in the last section. Basically, we're going to say we know that from the recursive formula, we have been told that ak is 5ak minus 1. So ak is 5ak minus 1 minus 6ak minus 2. So this was given to us with the definition up here, and this works for every integer greater than or equal to 2. So it works for everything basically. But I'm not really interested in knowing information about ak. I want to know information about ak plus 1, so somehow I need to change that. And so I can do this very easily by replacing k with k plus 1. Replace k with k plus 1, and what do I get? So this is what I get. And so cleaning up a little bit more, I end up with ak plus 1 equals to 5ak minus 6ak minus 1. But the inductive hypothesis gives us information about ak, and it gives us information about ak minus 1. As a matter of fact, it tells us that ak is equal to all of this right here, 5 times 3 to the power of k minus 3 times 2 to the power of k. So we can make that substitution, and similarly, we can get information about the ak minus 1. So I'm just going to record that on the paper over here. So ak is actually 5 times 3k minus 3 times 2 to the power of k. And also, ak minus 1 is a similar format. It's 5 times 3 to the power of k minus 1 minus 3 times 2 to the power of k minus 1. How come? Why do we know this? We know this because both k and k minus 1 belong in this list of numbers, and so therefore the theorem is true for those indices. So that means the terms can be rewritten with powers. We're going to take that information and plug it down here, and let's see what we get. So making the substitutions, we get this wonderful new formula with all the different colors for ak plus 1. So we are now ready to go ahead and do a lot of algebra to basically break it down. So there's a bunch of different ways of doing this, but I'm going to go ahead and multiply the 5 with the 5, multiply the 5 with the 3. When I do that, I'm going to end up with 25 times 3 to the power of k minus 15 times 2 to the power of k. And I'm just going to multiply also again the 6 with the 5. That's going to be 30 times 3 to k minus 1. And then again, 6 times negative 3 is going to be positive 18 times 2 to the power of k minus 1. Now, just keep in mind, what does it mean to write down k minus 1? So what does it mean to write down 3k minus 1? Using exponent rules, I can interpret it as 3 to the power of k, all divided by 3 to the power of 1. So I'm going to go ahead and do that for the 3k and for the 2k minus 1. I'm going to rewrite them in this following way. And so if I did that, what would I get? So there we have it. If I rewrite it, I'm just going to have a bunch of fractions at the very end. And I'm doing this because now I can take advantage of the fact that there's a 30 on top and a 30 on the bottom. There's an 18 on top and a 2 on the bottom. We can do some cancellations, basically. We can reduce the lowest terms. And if we did that, so we get the 10 and the 9. Because 30 divided by 3 is 10 and 18 divided by 2 is 9. But at this point, we have some like terms. As a matter of fact, we have 25 3k minus 10 times 3 to the power of k. Those are both like terms. So when we're adding them, we're going to get 15. And then we have 15 to the power of k plus 9. And we're going to go ahead and again combine them together to see what we get. So 15 times 3 to the power of k minus 6 times 2 to the power of k. But keep in mind, 15 itself is literally 3 times 5. And 6 itself is 3 times 2. So I'm gonna basically borrow this 3 and put it into that 3. And I'm gonna borrow the 2 and put it into this expression. Using the power rules, this is perfectly legal. If I did that, I would end up with 5 times 3 to the power of k plus the other extra 3 minus, instead of 6, now we have the 3. And then we have the 2 to the power of k plus the extra 1. And this is what we wanted to prove in the first place. This was our goal. And so we are finished with the problem QED.